Good morning, class. I hope you can catch up with this lecture or review this lecture later on, uh, or watch this lecture later on when you have time. Sorry for the delay. I had to fix some of the blinking problems of my um, my software. The StreamYard is when I actually connect to StreamYard, this blinking would occur. So anyway, to start with, the lectures will be again. First, before that, I'd like to again tell you about the main reference of this lecture. We are using Introduction to Quantum Mechanics by David J. Griffiths, and this book is recommended for you. So in this chapter, we'll go with the formalism, and we start with linear algebra for quantum mechanics. So most notations, most of the um, mathematical backgrounds are discussed in this chapter. So we'll be dealing with uh, the the linear algebra, and where we generalize the scalars to be complex, and then we're going to generalize into more than 3 dimensions. So we start with vectors. Um, Earlier on, we know that vectors are in 3 dimensions, like those vectors in the Cartesian space, where you have a component along the x, along the y, and along the z. But in general, vectors could have dimensions greater than that. So a vector space consists of a set of vectors, alpha, beta, gamma, and so on, together with a set of scalars, a, b, c, and so on, which are subject to the operations vector addition and scalar multiplication. Um, So here you can add 2 vectors. The vectors are denoted or represented by this symbol for a vector alpha, labeled alpha. So you have 2 vectors here. So alpha and beta, you can add them, and then you can produce another vector, gamma. And as you know, the 2 vectors could be added commutatively. This means that you can interchange the order of the addition. And this is also associative, meaning that you can add the second and third first, or you can add the first and second, or the first and the third first before you add the other vector, and you'll get the same result. There is a 0 vector whose components are all 0. Um, we call that the null vector or the 0 vector, in which when you add to a vector, it gives you the same vector. So say for example you have a vector alpha, you add a 0 vector, then it gives you alpha. Then there's also an inverse vector. We call that negative alpha, such that when you add it to um, the vector alpha, it gives you a 0 vector. So in three-dimensional case, you have a component along the x, y, and z, and the negative of that vector is that um, the components of the negative of that vector would be having opposite sign with the original vector. So there's also a scalar multiplication to the vector. So you have if you have a vector alpha, you multiply it with a scalar, then it gives you another vector of norm. Oh, norm is another word for magnitude of a vector, and the norm could be greater than or less than the original, depending on the scalar that you multiply, or could be also complex. It could also be because a could, in general, is a complex scalar. It The scalar multiplication is also distributive. Remember that a here is just a number, while the alpha and the beta are vectors, and they have components depending on the dimension of the vector. If you have a three-dimensional vector, you have three components. If you have five-dimensional vector, then you have five components. A is just a number, and it's just a number, just one number. So A could be distributed vectors like this. So A times alpha. A times alpha plus beta is just equal to A times alpha plus A times beta. This is also distributive, the scalar multiplication. So if you have A plus B here, um, I'm sorry, distributive with respect to a scalar. So if you have A plus B, two scalars, multiply to a vector, then that's just equal to um, A times alpha plus B times alpha. In this case, you have two scalars, A and B. It's also associative in terms of scalar multiplication. So you can multiply B, here the ordinary number B, to the vector alpha, or you can multiply A and B first, then you multiply it to the vector alpha, gives you the same result. So this one is an expression of a linear combination of vectors. So you have A times alpha plus B times beta plus C times gamma and so on. These are this is called a linear combination of vectors. Linear combination of vectors. Um, a vector lambda is linearly independent of the set alpha, beta, and gamma if it cannot be written as a linear combination of them. So, for example, in three dimension, you cannot write a vector k in terms of I and j, or you cannot write a vector I in terms of j and k, or so with j in terms of I and k. So those are linearly independent, meaning they have different direction. They cannot be written in the direction of the other vectors. So I is independent of j and k. It cannot be written in terms of j and k. So that's what you call linearly independent vectors. I, j, and k are linearly independent vectors. So if a vector lambda, in this case, is linearly independent to vectors A, alpha, beta, gamma, and so on, if it cannot be written as a linear combination of them. So remember, if you have um, a vector that cannot be written in terms of other vectors, then it's linearly independent. So this is the statement here. A set of vectors is linearly independent of each one, is linearly independent of all the rest. So there's also another statement here. Um, A collection of vectors is said to span the space if every vector can be written as a linear combination of the members of this set. For example, in three dimension, uh, in three dimensions you have ijk, and in three dimensions you can write the vectors uh, in terms of ijk, for example. So the ijk span the three-dimensional space. That's what it means. So for four-dimensional space or five-dimensional space or multi-dimensional space, you have if you have n-dimensional space, and you have n vectors that span that space. In three dimensions, you have ijk spanning the three-dimensional space. A set of linearly independent vectors spans the space is called the basis. So for example, in three-dimensional space, you have ijk. It's called the basis of the three-dimensional space. So other dimensional space greater than 3 would have to be spanned by a set of n vectors with n dimensions. So the number of vectors in any basis is called the dimension of the space. So for example, for three-dimensional space, you have three linearly independent vectors I, j, and k. That's the dimension of the space. So three linearly independent vectors, so you have three-dimensional space. A space with n dimension has n linearly independent vectors that span the space. So in this case, in general, for n-dimensional vectors, you have this unit vector. I mean, this linearly independent vectors, and you can write any vector in that space. You call that n-tuple. You can write that in terms of this expression. So for a vector in three-dimensional space, for example, A, you have A1I, A2J plus A3K. In this case, you have an n-dimensional, so you have A1, 2, 3, 4, 5 plus AN, EN, and so on. Or you can also you can write in like this, or you can also write it like this. It means that you have A1, A2, AN as the components of this vector alpha. To add vectors in n-dimensional space, you have the components of the vectors. Then you can add two vectors by adding corresponding components. So for alpha, you have A1, A2, A and until AN, and for beta, you have B1, B2 until BN. So for the sum of alpha and beta, you have to add corresponding vectors. So you have the first component as A1 plus B1, the second component as A2 plus B2, and the nth component would be AN plus BN. And if you multiply a scalar, just multiply each component by that scalar. This scalar is again, in general, complex. This C, this scalar C here is again complex. So C times A. So all the components have to multiply to C. The null vector, as I've said earlier, is a vector with 0 components. with all 0 as components. The negative vector has as a components negative of the original. The components of originally alpha is like if alpha is -5 e1 plus 3 e2 plus 4 e3 minus minus 2 e4, then the negative of that alpha would be 5 e1 minus 3 e2 minus 4 e3 and plus 2 e4, for example. So it's just a negative. You just have to multiply -1 to the components of the original vector. So here's a problem. Consider the ordinary vectors in 3 dimensions with complex components. Does the subset meaning it's a set within a set? I think you know the meaning of a subset. Does the subset of all vectors with AZ equals 0 constitute a vector space? If yes, if so, what is the dimension? If not, why not? Is it a vector space? Wait.
It's currently 11:45.
Yes. The answer actually for A is yes, but you have to explore that. You can solve this on your own. How about the subset of all vectors whose component is 1? So is it a subset? So you can find out. Does it follow the addition rule or the multiplication rule? How about the subset whose components are all equal? Is it does it follow the rules of a vector space? So you can explore that on your own. Here, this problem consider the collection of all polynomials with complex coefficients of degree less than n in x. So this is like x to the 0, x to the 1, x square, x cubed, x to the 4th, x to the 5th. So those are the collection of polynomials. So you can also explore this. You can also explore this question for that. How about this? How about that? You can ask about yourself about this. So you can explore these problems on your own. There's also another problem here. Prove that the components of a vector with respect to a given basis are unique. Of course, they are unique. So for for a vector space, you have an inner product of the vectors. Let's look at the vector space first. Going back. These vectors have inner products, so you can get the inner product of one vector to another. So here is just, you're just multiplying a vector to a scalar. How about multiplying a vector to another vector? So there are two types of vector products. Ordinarily in 3 dimensions, you have that product and cross product. But this cross product is still, although there are attempts to to have the cross product for n dimensions, but uh, it's still on in the process of development. But we are certain, we are sure that that product is um, has has an associated inner product for higher dimensions. But the cross product is only valid for now. It's only valid for some dimension, but not extended yet to n dimensions. But that product can be extended to n dimensions. So the inner product of two vectors, alpha and beta, here is denoted by. So if you get the inner product of this, it's written as that one, the bracket, uh, or this is called the ket notation of the inner product. Ket, K-E-T, ket notation. So you have this as a notation, and in some other references you can find this, but it's the same as this. So anyway, in this book, we're using the dot product or the inner product to be uh, alpha, beta here, the bracket notation. This is the ket. This is called the bra, and so that's why they're combined. There, it's called the bracket. So when you interchange the the order of the inner product, if you put beta ahead of alpha, then that would have to be operated with a conjugate. So alpha beta, the inner product of alpha beta is just the conjugate of the inner product of beta alpha. And alpha, the inner product of a vector to itself, is always greater than 0. And alpha, the inner product of alpha equal to 0 implies that alpha would have to be 0. Alpha to itself. And here you have alpha multiplied to a scalar times the vector beta and times the scalar c multiplied to a vector gamma, then this one is a valid multiplication. That's distribution. That's distributive property of the inner product. In the this is the problem that I'm talking about. It's blinking. I'm sorry for that, but maybe in the I don't know what's the reason for this, but anyway, the norm of the vector is like the magnitude of the vector. In three-dimensional case, you have the magnitude of that vector is just the square root of the inner product of the vector to itself. So if the unit vector, if you have a unit vector whose norm is equal to 1, then that's said to be normalized. That's said to be normalized. And two vectors whose inner product is 0 are called orthogonal vector. So orthogonal means perpendicular. vector. So they are perpendicular. And if you have a collection of mutually orthogonal normalized vector, it's called an orthonormal set here. And if you multiply the vector with itself, that's just equal to 1. And when you multiply with the other vectors, it's equal to 0. Means if you have I and I here, it's equal to 1. And if I and j are not the same, then it's equal to 0. Those are mutually orthogonal normalized vector. Or that's what you call orthonormal set here. Orthonormal set. So with an orthonormal basis, the inner product of two vectors can be written in terms of, the orthonormal basis is always a requirement for a vector. Orthonormal basis, this means that it follows this this rule. So for two vectors, here the dot product would be, or the inner product would be this one. You just multiply the first component of the first vector, the conjugate of that, times the first component of the second, plus the second component of the first conjugate of that, times the second component of the second, and then the third component of the first, the conjugate of the third component of the first, times the third component of the second, and then you add them all. That's the inner product of the two vectors. So for the norm, you can also do that here. That's this one is just the magnitude, and for the components you can get by multiplying or by getting the inner product with one of the bases to the vectors here. Look. That one. For a dot b in 3 dimensions, you have ax bx plus ay by plus ac bz, or a dot a is equal to a square equal to ax square plus ay square plus az square, and the components ax you can get that by dotting I to A and then J to A, or and AZ of course here is K dot A. It is always convenient to work with orthonormal basis. So the requirement to work on vectors is that the vectors should be written, the components of the vectors should be written in terms of orthonormal basis set. That means like IJK, so if you dot two of the bases, it's always equal to 0. But if you add, if you dot the base, the one of the bases to itself, it should be 1. So in 3-dimensional case, you have cosine theta equal to a dot b divided by its magnitude, the product of its magnitude, and this is equal to a dot b over ab, where the theta is the angle between a and b in 3 dimensions. There's also an analog to n-dimensional what you call this vectors, like for example alpha and beta. there's an analog to that, which is although it's hard to imagine uh, how it's envisioned, the cosine, the angle between two n-dimensional vectors, but uh, you can you can use this formula to find it. Here, I just would like to present this Schwarz inequality to you. This is the inner product square of alpha and beta is always less than the product um, of the inner products uh, of the vector with itself. So here, this one looks like this one. This one looks like uh, here. This one looks like. By the way, these two, this inner product of alpha and beta and the inner product of beta and alpha, they are conjugates of each other. So you can also write this as alpha beta, inner product of alpha beta times the inner product of alpha beta, its conjugate. Or you can write this as conjugate of beta alpha times beta alpha. This is this one. So this one is just this one here. Because of the Schwarz inequality, you can actually get cosine theta, because this side, the right side is always greater than or equal to the left side. But don't imagine yet the angle theta between these two vectors, because it's hard to imagine for dimensions greater than 3. Now, suppose you start out with, this is a problem which you can do at home. Suppose you start out with a basis, this basis, for example, E1, E2, and En, and they are not orthonormal. You can do the Gram-Schmidt procedure to make them orthonormal and change them to this set. So first you have to do this. You know what this means. So anyway, you can try this procedure. You can try this procedure by doing these 3 vectors here. You can do the Gram-Schmidt procedure to orthonormalize the 3 space bases here. Just try it and learn from it. We have also a problem here to proving the Schwarz inequality, and then finding the angle. Of course, this is just 3-dimensional vectors, so you can actually think of the angle for these 2 vectors. Then I'm going to discuss about linear transformation, but I think I would have to wait for the next meeting because of this blinking problem of this this is of course due to the StreamYard, because if I do not use StreamYard, this would not blink. So I postpone the discussion to next meeting. So we'll start with linear transformation next meeting. I'm sorry for this problem, but next time I hope it won't recur. So thank you for listening. I hope you learned something today, and I'll put the link of this lecture to our Google Classroom and Molly Room. Take care.